Hey board physicists.
1.5 Momentum. As we saw in equation 1.17, for a particle in state psi, the expectation value of x is given by this equation. What is this expectation value? Note that it is not the average when you measure the position of the particles repeatedly, because the first measurement will collapse to a spike at the value obtained, then the subsequent measures will give the same results if the subsequent measures are made quickly enough. So what is it then? The expectation value is the average of the measurements performed on all particles in state phi. This means after we make the first measurement, we would have to find a way to return the particle to the original position and then make more measurements. Then we would have to take the average of these results. Or it means we prepare a whole ensemble of particles in the same state psi to then measure the positions of all of them. Then we take the average of these results. To make sure we understand this, let's use an analogy. Imagine a row of bottles on a shelf, each containing a particle in the state psi. A student is assigned to a bottle, and at the same time each of them measure the position of the particle using a ruler. Then the average of these positions would give the expectation value. The more bottles, the closer to the expectation value. To summarize, the expectation value is the average of repeated measurements on an ensemble of identically prepared systems, not the average of repeated systems on one and the same system. Since psi is a function of time, the value of the expectation of x will change as time goes on. So we can differentiate the expectation value with respect to time using equation 1.25 and 1.28 to get this. Is the fact that dx over dx equals 1, and we throw away the boundary term since psi goes to 0 as x goes to plus or minus infinity. We perform another integration by parts and finally get this is the velocity of the expectation value of x, which is not equal to the velocity of the particle. Because if the particle does not have a determinate position prior to the measurement, neither does it have a well-defined velocity. All we can do is find the probability of getting a particular value. Stay tuned for chapter 3 and we will see how to construct the probability density for the velocity given psi. For now, we just accept that the expectation value of the velocity is equal to the time derivative of the expectation value of the position. We can now use this to work out the momentum, which equals mv. Therefore, the expectation of the momentum is given by this. We can rewrite the expectation values of the position using psi and its complex conjugate, such that conventionally the operator is sandwiched between conjugate of phi and phi. So we can see the operator x represents the position and the operator h bar over I d dx represents the momentum. But what about other dynamic variables? Well, all quantities can be written in terms of position and momentum. For example, kinetic energy is expressed like this, and angular momentum can be expressed by this. So to calculate the expectation value of these quantities, we simply replace every p by the operator that represents it. We replace p by h bar over I, partial derivative with respect to x. Then sandwich it in between phi and phi conjugate, and then integrate. For example, if we take the kinetic energy, we can rewrite it as this. So in general, the recipe for calculating the expectation value of any dynamical quantity for a particle in state psi is given like this. So we can see that the expectation value of x and the expectation of value of p are special cases of this equation. This general equation represents the expectation value of q and is a radically new way of doing business compared to the classical mechanics. Practice will help understand it better. We will be doing videos covering these problems, and this question can be treated as an axiom if need be until chapter 3. To do this, we first need to try and visualize how the wavelength and the position depend on each other. Why, you might ask? This will become clear in a second. Imagine a rope. This rope is very long and you are holding one end of the rope. You generate a wave by shaking it up and down periodically. Now, if someone was to ask the question, where is the wave precisely? We would think that it's a bit silly. The wave can be anywhere over the length of this rope. If they asked us what the wavelength is, we could give an estimate quickly, after examining what it looks like. Let's say about 1 meter. Now if we take the same rope and give it one sudden jerk only, the wave would move with a narrow bump. And then if someone asks the same question, where is the wave, we could easily give an answer. But if they ask us what the wavelength is, that would seem a bit silly. Since the wave is not periodic, how would we give a wavelength to it? If we really wanted, we could draw cases that were somewhere in between, but we would quickly realize that we can only have one of the two things, a defined wavelength or a localized wave. This can be explained using Fourier analysis, which would give a more mathematically rigorous argument, but for now we shall stick to the qualitative argument. This phenomenon applies to any wave function and therefore is also applicable to the quantum mechanical wave function. We know using the de Broglie formula we can associate the momentum with the wavelength. If there is a spread in the wavelength, there will also be a spread in the momentum. Therefore, a more defined momentum gives a less defined position. Quantitatively, we can say that sigma x dotted with sigma p is greater than or equal to h bar over 2. The sigma x is the standard deviation in x and sigma p is the standard deviation in p. This is the famous Heisenberg's uncertainty principle. We will prove this in chapter 3. Stay tuned. So what is this principle? Essentially, it's saying that we can try to define what the wave is by obtaining a localized spike, but we have a trade-off. The momentum measurements will be widely scattered, or we can try to produce a reproducible momentum by making phi a long sinusoidal wave, but we will no longer know the position precisely. It will be scattered. We can try to make a system with both the position and momentum scattered, but there is not much to gain in that. Equation 1.40, Heisenberg's uncertainty principle, puts no limits on how big sigma p and sigma x can be. And that's the end of the chapter. 1. Bored physicists